So back in chapter 4, we were talking about some of the early attempts at models of atoms. Let's look at how the model of the atom has progressed from the beginning to where it is today. So remember John Dalton, the inventor of the atomic theory? He pictured atoms as solid spheres that were indivisible and complete in themselves. So picture just a solid sphere, like a ball. That was John Dalton's attempt. Obviously incorrect. Then came J.J. Thomson. He discovered the electron using his cathode ray experiment. He excited electrons in these cathodes, and they shot out these rays, which we now know are electrons. And he deduced that they were negative because they were pulled towards the positive plates and repelled by the negative plates. So he said that the new model is going to include positive and negative parts that were needed. We now know there's more to an atom than just a single sphere. So he proposed a model of an atom that consisted of a solid, positively charged particle sphere with negative electrons embedded in the surface. Remember, we called it the plum pudding model. And this is what it looked like. So picture a sphere. The middle part, the pudding part, is positively charged, and those negative electrons were just scattered throughout. Then came Ernest Rutherford with his famous gold foil experiment. Remember, he shot the alpha particles at gold foil and watched the backscattering on the detection screen. Well, it showed that electrons were located outside of the positively charged nucleus in the middle of the atom, and that nucleus was very small and very dense. So he made a model called the Rutherford model to reflect this idea. And it looks something like this. We have the nucleus in the middle, and we had the electrons floating around in the space outside of the nucleus. Then came Niels Bohr. He realized that the Rutherford model didn't explain some of the chemical properties that atoms had. So he proposed a model of the atom in which electrons revolved around the nucleus in circular orbits like planets around a sun. His model looked a little something like this. He was wondering why electrons didn't fall into the nucleus. If they were rotating around the nucleus and the nucleus was positive and the electrons were negative, eventually they would come crashing into the nucleus, like a satellite crashes into the Earth when it loses its orbit. He theorized that electrons moved in different orbits and that those orbits were at different levels. And a large amount of energy separates one from the other, a very specific amount. He called it a quantum of energy. So as the electron orbits, if it loses that specific amount, it goes to a lower level. And if it gains a specific amount of energy, it jumps to a higher level. And that helped explain some of the chemical behaviors of atoms during chemical reactions. So his model said that the energy level of an electron can be compared to rungs of a ladder. So if we have a ladder here, and this sphere represents you on the ladder. You can be on one rung or the other. You can climb from one to the other. You can even climb lots of steps at a time. You could climb down the ladder from rung to rung, but you can't float in the middle. It's impossible to be in the middle of the ladder. You're either on one rung or the other. So just like in an atom, an electron can't exist between energy levels, just like you can't stand between the rungs of a ladder. You need a quantum of energy, which is the amount of energy required to move an electron from one energy level to the other to jump energy levels. Unfortunately, this could only explain the behavior of a hydrogen atom. But it did lead to the development of the quantum mechanical model of the electrons and atoms as we know it today. So the quantum mechanical model says that energy is quantized. It comes in chunks, like Niels Bohr said. Quantum is the amount of energy needed to move from one energy level to the other. And since the energy of an atom is never in between, there has to be a quantum leap in energy to make those jumps that explain some of the chemical behavior we'll be talking about later. In 1926, a scientist by the name of Erwin Schrödinger, and we'll talk more about him in class, he derived an equation that described the energy and position of electrons in an atom. Don't worry, you don't need to memorize or use this equation. It's a very complicated physics equation, but basically, if you boil this equation down, it tells you the probability of finding an electron along a single axis of space. And this is the basis for the quantum mechanical model of the atom. If you apply the math of Schrodinger's equation to the electron positions, you start getting all these really crazy shapes that we'll be talking about later in this chapter. So the basics of the quantum mechanical model is that things that are very small, like atoms and electron orbits, behave very differently from things that are big enough to see, like planets revolving around the sun. So it's important to note that the quantum mechanical model is a mathematical solution. You can't see it, and it's very hard to test outside of mathematics. But what it does tell us is that there are energy levels for electrons. Unlike what Niels Bohr said, the orbits are not circular most of the time. And it can only tell us the probability of finding an electron a certain distance from the nucleus. A good analogy here is this fan. If I turn this fan on and the blades start moving, you know where the blades are. You see this blurry area of where the blades are and kind of where they're going. Just like in an atom, there's a blurry electron cloud of where the electrons are, but they're constantly moving, so they might be in that area, they might not. If you could stick your finger in this fan really quick and pull it out, you may get your finger hit by one of these blades, but you might just go in between the blades. So you have a high probability of getting your finger hit by these blades if you stick it in. But if you do it really quick, you may not. It depends on when and where you're touching. So that's kind of the analogy that we're talking about here. There's an area, we call it the electron cloud, and according to Schrodinger's equation, this is just where there is a high probability of finding an electron in that space. So this is an artist's representation of the electron cloud. You can see the nucleus in the middle, and the spherical space around it is just where you have a higher probability of finding an electron. So the concept of what an atom looks like has changed as new information about atoms have been discovered. Although our current understanding about atoms comes from the quantum mechanical model, we're still going to sometimes refer to atoms more like the Bohr's model for simplicity throughout this course. But it's important to know that it's not exactly the way it looks. Basically, when you're thinking about the model of the atom, you just need to know that there are protons and there are neutrons, and they're in the middle in the nucleus. It's a very small, dense region. And then you have electrons, and they're located somewhere outside the nucleus. And that space we call the electron cloud. This can get really complicated, as you're going to see further in this chapter, but don't worry, you don't need to know it on a quantum physics type level, but it's important to know the reality of what we're dealing with here. So in the next couple of videos, we're going to delve more into electrons and where they are and how they work and why they're important.